Good morning, you guys. Let's do a review. Chapters 1 through 3. So first off, Chapter 1 is all about Euler. Euler is about edges, and this should be relatively easy. At least it's easy in the fact that mathematicians view the problem as a relatively easy problem. It doesn't mean that implementation of it is necessarily easy. What are we going to do from Euler? Well, first off, we're going to ask about Euler circuits and Euler routes. Now this makes use of Euler's theorem. It's going to use green there, and it just died on me. Try another one. Euler's theorem, which is a really neat theorem. It tells you about the existence or non-existence of Euler routes and circuits. But it doesn't tell you how to build them. So Euler's theorem says we start with a connected graph. So it can't be a map of Hawaii and a map of Maui, and you expect to find a circuit around Maui and Hawaii without a road between them. You have to have a connected graph. And then all you do is you look at the valences. All even, then you have the Euler circuit. Exactly too odd, then you have the Euler route. And else, nada. You don't have an Euler circuit, you don't have an Euler route. But notice, this as it being what we call an existence theorem, it doesn't tell you how to find them or where they are. You just have to guess and check. So here's one of the examples of a graph. Where we would ask you to maybe look at it and just tell us, does it have an Euler circuit? Does it have an Euler route? And if so, tell us how to find it. Well, let's take a look at this. Ready? There's a valence 2, two edges coming in. Here's a valence 3. At that point, I know the best we're going to have is an Euler route. Valence 2, valence 4, valence 2, valence 2, valence 3. So in this situation, we have exactly 2 odd valences. This implies the existence of an Euler route. Now what's special about the route is you have to start one of the odds. Now we just go to the map and we're just going to write down possible route and see how well it goes. Now I'm going to highlight as we go along because that's useful. So here we go. I'm going to start here. And I'm going to call this 1. I've just driven from one vertex to the next. And now 2. Now 3. Now 4. We've reached the other odd vertice, but there's edges that we've missed. So we're just going to continue. 5. 6. 7. 8. 9. And if you look at we have completed it. We are to the other vertex, the end. And that's how we just guess and check, and we try to make it happen. It is possible you could fail, but then you have to use the decimal point system where you have this route, 1, 2, 3, 4, and you modify it maybe to 1, 2, 2.1, 2.2, 2.3, and then you pick up a 3 because you missed these that went off a vertex. That's a common method to use. Now, Euler means you're visiting edges. Examples of this is a route for a specific garbage route or a snowplow route. Now, people might wonder, well, a snowplow route. Here's roads, but don't we have to go on those roads more than once? Okay, let's indicate that by putting 2 edges between here. And maybe this one 3 because it's extra wide, and this one 1 because it's a small one, but this one 2, and this one 3. Guess what? That is, for each edge, the process of snowplowing part of the graph. And guess what? It's exactly an Euler problem. Each edge represents 1 pass on the correct side, and it is still an Eulerization. We like to ask questions about this, the model application of the process. Now, because Euler is associated with real life problems, sometimes Euler's theorem says no, but you still have to do the problem. Why? Because you have to snowplow the route. You just don't do it in such a way that you get to cover each edge exactly once. So you have to be willing to Eulerize. And here's where we get our first optimality. When you Eulerize, then you can ask, have you done it well? What we do is we use duplicate edges. And so here's a very simple street network. It has exactly 2 odd valences, and if I duplicate this edge, it is now a graph that has an Euler circuit. Because the number of odds divided by 2 was the dupes used. 2 odds divided by 2 is 1. I used exactly 1 dupe. I can conclude this is an optimal Eulerization. I did as best I could. But the larger graphs, frequently we cannot get exactly that many dupes used to Eulerize. Now, here's a good test question. Why don't we do something like this ever? And the answer is, we don't get to create roads that don't exist. The snowplow does not get to go through your backyard, which is probably good. All right. Now, chapter 2 takes a little bit of a turn. Chapter 2 now focuses on vertices. So now we're trying to visit vertices. Now this is called a Hamilton problem. And Hamilton is hard. And because of this, we use algorithms. We use algorithms to try to answer the questions. Now, in general, a Hamilton problem is only done on complete graphs. Why? And the reason is complete graphs allow us to always be able to complete one of our algorithms. And so the graphs that we work with often have lots of edges and lots of vertices, but I want you to remember that's not a vertex. That's just a crossing point in the graph. And because Hamilton problems are associated with traveling, usually a traveling salesman problem called a TSP, we weight the edges. Now we can also weight the vertices. Some vertices are more expensive than others, etc. But we restricted ourselves to just this. Now the algorithms that we use have certain properties. The first, the nearest neighbor algorithm, is an algorithm that is greedy because it tries to use the least right off the bat, or spend the least amount of time, or have the most nap time, something that is an optimal answer question. But it is also local. It does not make use of all of the information right away. In fact, the nearest neighbor algorithm has a starting point which you can maybe randomly pick or be forced upon. It's very quick. It's easy to figure out. You're here, where's the next nearest one? Because these graphs can be really complicated, we frequently give you a table in which to run them. Hence, I can set up a very large table, a 10 vertice table with a 10 by 10 and a bunch of numbers, and it's not hard to run the algorithm. So why is it so important to know the difference between the nearest neighbor algorithm versus the sorted edge algorithm is that the sorted edge algorithm is a greedy algorithm. But what's important about it, it's global. It tries to make use of all of the information, every step. It's not nearly as fast because you have to consider, you have to compare, you have to think. Local algorithms usually are algorithms that can have the same property, but anytime you require more cognitive effort, one would expect them to produce better answers. But neither of these algorithms have, as I say, a dead man's name associated with it. Neither of them are known to produce the best answers. In fact, it is very hard to ask the following question on a traveling salesman problem. Is our answer optimal? In fact, usually we don't even ask that question. Now we can compare two answers and say one is better than the other, but the best doesn't have to be optimal. Best is just the best of those two. Optimal means, in some sense, the best of all. Now the sorted edge algorithm has a little quirk to it, and that is sometimes you can't pick a very specific edge. And the reason for this is that as you develop your route, and say you pick these two, you might now want to pick this one because it's the next least edge in all of the edges you're looking at. But that one's not allowed because no circuit looks like having valence 3. Circuits look like this. You go in and you come out. So the sorted edge algorithm has greater complexity. And that means it's kind of harder to get the right answer. In addition, because you're not really anywhere to start, your choices of edges could be pretty funny to beginning with. You could have chosen these 4 edges out of a graph that has tons of vertices. They're not even connected yet. They're not starting to create a circuit. And so you have to be aware that you are nowhere in the situation. Now when we're done, we in general like to just write them in some order. A goes to C, goes to F, etc. And we'll ask you to do that. And this is something that is not terribly hard. You might, in the end, discover, oh, this is my route. But I might ask you to start it at G. And so you got to look towards G, and then go in one direction or the other. There are 2 good answers starting at G. So there's not just one answer to a sorted edge. You can have very many answers, all being correct. Now, it turns out that the sorted edge algorithm has a unique modification that if we remove the desire for a circuit and we start searching for a tree, then the algorithm becomes a minimal spanning tree algorithm, and it's called Kruskal's algorithm. Kruskal's algorithm has a dead man's name associated with it, which means it produces wonderful answers. Now the problem with Kruskal's algorithm is frequently ask you to add up the values to say what's your answer. And you got to make sure you use your calculator well, but I am going to point out how I don't mind answers to be written so that you don't find yourself frustrated on the exam. Let's take a strange graph here. I'm going to give lots of edges. And now I'm going to put in lots of weights. 3, oh that's terrible. 4, 6, 7, 5, 8, 6, 7, 4, 5, 9, 8, 6, 4, 9. I think I have all the edges weighted. A A typical question associated with Cruxell's algorithm is to create a utilities map so that water flows or electricity moves, and we want no circuits. Since it's a modification of the sorted edge algorithm, all you simply do is you look for the smallest edge out there and you make use of it. So I'm going to start with that 3. Then I'm going to pick a 4. I'm going to pick a 4. But I can't pick that 4 because I have a circuit. All the 4s are done. Now I'll pick a 5. Here's a 5. Here's a 5. There's a 5. So you can see, like the sorted edge algorithm, you really don't have anything connected at all. It's just building something. In this case, it's building a tree. We're keeping away from circuits. Now I can pick the 6s. Can't do that one. It would make a circuit. I can do this one. I can do this one. Ooh, we're getting very close. Look at this. All of the vertices, except for one, have been visited in this tree, but it's not fully connected yet. Now when we go to 7, ooh, look at this. Now all of this is connected. And here's the last 7. And I want you to notice that every vertex is connected via this tree. At this point, it's done. And one way to say how good is this one, you can say the minimal answer is, and now you can simply say 3 plus 4 plus 6 plus 7 plus 5 plus 6 plus 5 plus 4 plus 5 plus 7, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's your answer. If you want to take out your calculator and calculate it, great, but I will grade your ability to add. Hate to say it. Use a calculator incorrectly, so just leave it there. And this picture is super. This picture just shows me exactly what you've done. All right, now comes 2 of the algorithms that are kind of long, and they are the list processing algorithm and the CPA algorithm. I have given you on the review a problem to work on. There is going to be a complete list processing problem, and there's going to be a complete CPA problem. The list processing algorithm actually creates a schedule. The CPA algorithm creates a priority list. So they do different things. The CPA creates a priority list to run on the list processing, and the list processing uses some given priority list. So in general on the test, you can fully expect that I will give you a priority list for the list processing question, and I will specify the number of machines. That way I can test your ability for the list processing algorithm. Then I might also say, okay, ignore your resultant answer. Let's create, using the CPA, a new priority list for that problem that we've just done. And I won't ask you to rerun the algorithm. I just want you to create a priority list. All right. Last but not least, bin packing. Now for the bin packing, I am going to use the names. So the first packing algorithm is called next fit. It is local, it is fast. Then comes first fit. It is local, it's fast, but it has more open bins. So it's probably better than that. But next comes worst and best fit. And the ideas of them is that they actually show there's something called a heuristic, what you're trying to achieve. Next fit, in general, speed. No, don't break the merchandise. Touch everyone and you move it one spot right away, nothing else. first fit is seemingly we're keeping things open, so we're probably trying for good packs at full bins. But it also preferences left, like we're packing the front of a semi. Worst and best, this one, best fit, seems to be prioritizing completely good packs. In fact, maybe perfect ones. While worst isn't worrying about that. It's actually leveling out the load. So there's actually some pretty good pictures of these. The first fit often works well with a semi where left is better than right and it levels off. Best tries to do something like this and then it has a few other strange ones with lots of full. But worst doesn't worry about full. Instead, it tries to get level. All right. Those are the questions that are going to be on the exam and none other.